Welcome to FrontEnd Systems Lab. This is a channel where we go under the hood of modern computing systems, not the surface explanations, not the simplified diagrams, but what is actually happening underneath the hardware. Today we're looking at GPUs and the architecture behind modern graphics. Most people think a GPU is just a faster CPU for graphics, but that is not correct. A GPU is a massively parallel execution system. It does not focus on one task at a time. It runs many tasks at once, and everything you see on screen is built from that structure. So let's break it down. Chapter 1. Parallel execution. At the core of a GPU is parallel execution, not speed, parallel work. Thousands of small operations running at the same time. Work is split into threads. Each thread handles a small part of the problem. Then they all run together. This is SIMT execution. Single instruction. Many threads. One instruction is issued, but it runs across many threads at once. There is also SIMD behavior, where the same operation is applied across large data sets. Threads are grouped into warps. A warp runs in sync. All threads move together through the same instructions. If one thread waits, the system does not stop. It switches to another warp. This is how latency is hidden, not removed. Hidden thread blocks are assigned to compute units. Each unit runs many warps, and the system constantly balances workload. The goal is simple. Never leave compute units idle. If there is space to compute, something will run, always. That is the foundation of GPU performance. Chapter 2. Memory and data flow. Now we move to memory, because compute is only half the system. The other half is data movement. Global memory stores large amounts of data. But it is slow, so GPUs use layers. Shared memory is closer to the cores, faster but limited. Registers are the fastest, used for immediate work. Caches sit in between. L1 cache is local to compute units. L2 cache is shared across the GPU. These layers reduce waiting time, but the real optimization is in access patterns. Memory coalescing groups data requests together, so threads access data efficiently. Instead of scattered reads, prefetching loads data early, before it is needed. While one group waits for memory, another group is already computing. This is the key idea. The GPU never waits, it switches work. Compute and memory always overlap. Chapter 3. The graphics pipeline. Now we reach what people actually see, the graphics pipeline. This is where data becomes images. Everything starts with vertices, points in space. These are transformed into 3D positions, then shapes are built, then rasterized into pixels. Each pixel is processed individually. In parallel, fragment shaders calculate color, lighting, texture, depth testing decides what is visible, stencil operations handle masking. Textures are applied across surfaces, then everything is blended together. Finally, the framebuffer collects the result and sends it to the screen, but this does not happen once. It happens continuously. Every frame is rebuilt from scratch, 60 times per second or more. Nothing is stored as an image. Everything is computed again. Chapter 4. Beyond graphics. Modern GPUs are no longer just for graphics. They are general compute systems. Matrix math is a major example, used in AI and machine learning. These operations run extremely well in parallel. Deep learning training uses thousands of GPU cores, each updating part of a model at the same time. Inference runs in real time. Physics simulations also fit this model. Each particle becomes a computation. Video processing is parallelized across frames. Scientific computing uses GPUs for large simulations, fluid dynamics, molecular systems, large data transformations. Anything that can be split into parts can be accelerated. That is why GPUs became central to AI, not because of graphics, but because of parallel structure. Chapter 5. Scheduling and control. But none of this works without coordination, so GPUs use scheduling systems. Work is divided into blocks. Blocks are assigned to compute units. Threads are constantly balanced. If one unit is busy, work is shifted elsewhere. If another is idle, it receives more work. Kernels define work groups, but they are broken into smaller execution units. The scheduler controls timing and manages execution order. If one task stalls, another replaces it instantly. This creates continuous execution, even though everything is constantly switching underneath. The goal is occupancy. Keep all compute units active at all times. Chapter 6. System integration. The GPU does not operate alone. It is part of a larger system. The CPU sends instructions. Drivers translate them into GPU commands. APIs like Vulkan and DirectX sit in between. they abstract hardware complexity. Memory is often shared now, between CPU and GPU, which reduces transfer delay. Multiple GPUs can work together, or even scale across cloud systems. Thermal systems manage heat. Power systems manage energy. Error correction ensures stability. So the GPU is not isolated hardware. It is part of a full computing stack. Chapter 7, Emergent Behavior. And finally, the most interesting layer, emergent behavior. GPUs adapt in real time. Clock speeds adjust based on load. Voltage changes based on temperature. If the system overheats, performance is reduced. If load decreases, efficiency improves. Drivers continuously optimize execution. Work is redistributed dynamically. The system is always balancing itself. This is why performance feels smooth. Not because it is fixed, but because it is constantly adapting, in real time, closing. So when you look at a GPU, you are not looking at a simple processor. You are looking at a layered execution system, built for parallel computation at massive scale. Everything you see on screen, every frame, every simulation, every effect, is the result of that system working together, not sequential processing, but thousands of operations at once. That is what is really under the hood. Thanks for watching Front End Systems Lab. Please subscribe for more under the hood content.